Okay, so the good news is that we've nearly finished T5. So there's just a couple of bits that I want to go through with you now, and I think the easiest way of doing that is by talking through these Yakka Pakka questions. Okay, so in 5.1, okay, we've got this question. We haven't had a chance to go through this in class yet. You should know this formula from my GCSE. Obviously that formula is complete rubbish. And then how do we get the other formulas down at the bottom? Well, we know that P equals V times I, and we also know that V equals IR. So there's a couple of things that we can do with that. We can substitute the V in there, and then we're going to get P equals I times R times I, which just simplifies to I squared R. Okay, so that's that formula there. That one works. So that one's obviously rubbish. And then the other thing that we can do is substitute for I instead, which will give us P equals V squared over R. Means that that formula is correct and that one's rubbish. And if you go and have a look in the data booklet, there are those three formulas, so you don't even need to remember them. Happy days. You do need to be able to use them though. So let's have a go at this question. The formula that we need is the connection between voltage, power and resistance. It tells you the power, it tells you the voltage, and it asks you to find the resistance, and if you rearrange that equation you'll find that resistance is 48 ohms. Here's another question to practice using the formula. It tells you the current, so we know that. It tells you the resistance, so we know that, and it asks you for the power, so the formula that you need is this one. So you do 20 squared times by 0.5. 20 squared is 400, times by a half is 200 units of power of watts, capital W. In this formula it tells us the current, and it tells us the resistance, and it asks us for the potential difference. That's the formula that you need. 2.5 times by 4. Even I can work that one out in my head. Getting a little bit more tricky now. Onto potential dividers. Okay, so at the moment this voltmeter here has got a resistance of more than 10 mega ohms. That's more than 10 million ohms, which means that when the circuit's turned on, very little current will flow through the voltmeter here. Okay, which means that there isn't any current flowing through it, so it won't affect the potential difference at this point, the voltage at this point here. And as you can see, this is just a potential divider circuit, so you put 9 volts in. Okay, so each of these resistors get an equal share of the voltage, 4.5 volts across this one and 4.5 volts across this one. This one's an LDR, which stands for a light dependent resistor, but don't let that fool you. Okay, the numbers are straightforward, 400 and 400, so they each take an equal share. If it's changed to an analog voltmeter though, okay, then we've got a different circuit. Now we can imagine that there's a 400 ohm resistor here, so it's not 10 mega ohms anymore. Okay, now it's 400 ohms. So now we need to think about how that affects the circuit. So what we've got here then is we've got a 400 ohm resistor in parallel with another 400 ohm resistor. So the total resistance of this bottom part of the circuit, all of this down here, the total resistance we need to work out like this. Now you might just be able to look at it and do it in your head because the numbers are very straightforward. I'm going to write it out in full so that you can see how it works. So it's going to be 1 over 400 plus 1 over 400, which is 2 over 400. So RT is 400 over 2, which is 200 ohms. Okay, and I said the numbers were easy. Okay, if you put two two identical resistors in parallel with each other, then the resistance just halves. So now what we've got is we've got a potential divider circuit. Instead of drawing all of this on the bottom, I can just cross that out and draw an equivalent resistor here, okay, that has now got 200 ohms. So now we've got 400 ohms on the top here, and we've got 200 ohms on the bottom here. So how's that going to affect the share of the resistance? Well, if you're Rowan, you might be able to work this out in your head, because the output voltage is going to be equal to resistor 1 over resistor 1 plus resistor 2 times by the input voltage, and resistor 1, which is the one on the bottom, the one that we're interested in, is 200 divided by 200 plus 400. Okay, so you can see it's just ratios. So that's 1/3 of 9 volts, and 1/3 of 9 volts is 3 volts. There's our answer. Here we go. This is just the sort of sneaky question that the IB love. I'm sure I nicked this from a past paper. If this ammeter has got negligible resistance, then it effectively means that we can forget about that resistor there. It's just like it's not in the circuit at all. So if this has got zero resistance, all the current will be flowing this way. None of the current will be flowing through here, which means all of the voltage will be dropped across this resistor here. So that will take all of the potential difference. And if you look at the numbers, you can indeed work out that that's the case. You can use V equals IR. You know the voltage, you know the resistance, and if you work that out, you should work out this current here. Okay, so now we're going to position that correctly, which means it goes in here. There's our ammeter, which means that now we have got that 500 ohm resistor in place. So now you need to work out the total resistance of the circuit. That's very easy, because the resistors are just in series with each other. So you just add them up, 100 plus 500, that gives you 600 ohms, and then okay, we know the voltage, the total voltage is across both of those resistors now, so we can use V equals I times R, where we're using the total voltage and the total resistance to find the current in the series circuit. That's 9 volts times by 600, and I'm not sure I can work that one out in my head. Okay, that gives us 0.015 amps, which is 15 milliamps. Okay, don't be confused with this one that it's a potentiometer circuit. Okay, we can redraw the potentiometer circuit if you want. It's exactly in the middle, which means we'll have a 1 kilo ohm resistor on the top and a 1 kilo ohm resistor on the bottom. Okay, and then there's another 1 kilo ohm resistor on this side. Okay, hopefully you can remember from the previous question that if we've got two identical resistors in parallel with each other, then the resistance just halves. So we can redraw this circuit like so. We've still got a 1 kilo ohm resistor on the top, but the equivalent resistor on the bottom now is just 500 ohms. There we are. And using the idea that we used in the previous question, the total voltage is the current times by the total resistance. We know the total voltage in, the current's what we're trying to find, and this is 1500 ohms. So the current is 12 divided by 1500, oops, 8 milliamps. There we are. Well done.